Thank you very much. And first of all, of course, thanks to Andrea for doing this very great job organizing the whole project, but of course the workshop. And I was not introduced in the CREEP involved in the CREEP project, but Andrea invited me to speak here, and I'm very happy about that occasion. So it's a great pleasure to be here, and I must confess I love the song of Radiohead, CREEP, and I also love the book CREEP, so I'm a creep. So I like to talk about CREEP, and that's what I'm going to do. So I would like to talk about a few aspects of coseismic loading and postseismic relaxation and the involved deformation. And so it's a project that I did together with my colleague Emily Garnets from Grenoble and our PhD student Felix Henschel. So we work on this specific shear zone. So I'm presenting a little bit of natural observations during this talk. And so the DAV, the Ferriger-Antholz-Falzer shear zone, is a major shear zone in the system of the Periadriatic line. And so it's a major shear zone where crustal blocks in general are moved over scales of tens and hundreds of kilometers. So we discussed a few things during this workshop on the different scales, the different temporal and spatial scales, and how to compare them and how to link them especially. And I just put here a little bit of a few keywords. And if you think of these large scale shear zones, we think of earthquakes. Of course, they are involved in big, large shear zones. We have earthquakes trigger transient deformation. We care about strain localization and non-steady state flow, but how is that linked to the large scale mountain building? So big shear zones move the crustal blocks over kilometers of scales, and then we have to care about the long-term flow and the long-lived shear zone activity and a steady state, at least at some time intervals we can assume that we have something similar than steady state. So how are these different processes on the different temporal and spatial scales linked? And before I take you to the Eastern Alps, I would like to summarize a few aspects on what we know about coseismic loading and postseismic relaxation below the seismogenic zone in the continental crust. So I'm focusing on this blue shaded area here for a special reason, because if we consider earthquakes within the seismogenic zone, we have an effect on the downlying area where earthquakes cannot nucleate, and that is below the base of the seismogenic zone, as is defined by, for example, Scholz et al. So I'm talking about large earthquakes that rupture the whole schistosphere and leave marked imprint in the rocks with below, in the uppermost plastosphere below the schistosphere. And why is that area so interesting? The area is so interesting because we do see systematic fluctuations in stresses, strain rates, and also pore fluid pressure. So that is that is a very summarized graph. So we can assume the maximum stresses within that area. That's why this area is so interesting. We can suggest and expect the highest stresses to occur exactly in that area, and we can expect the fluctuations after earthquakes. So the as we heard yesterday also, if we have earthquake, we have higher strain rates, so the brittle ductile transition is shifting to greater depth. And of course, during interseismic periods, during postseismic creep, it is going upwards again. So we do see systematic stress and strain rate fluctuations in exactly that area, and we also can expect systematic fluctuations in the pore fluid pressure, in the availability of fluid, because we create a porosity, an increased porosity. We create a fracture system coseismically, and then of course fluids can flow, and all sorts of reactions and healing processes get triggered. And what is the depth level of this area? Well, it's probably not the depth level, but it's mostly the temperature which is controlling the area. And typically, the base of the seismogenic zone is seismologically quite well defined to be the 300-degree isotherm. So we are talking about an area of green schist facies conditions. Okay, so before I take you to the Eastern Alps, firstly I would like to summarize a few things that we heard yesterday and what is known on this, what is the evidence of coseismic loading and postseismic creep. So I would like to summarize that. We heard yesterday a lot of observations, and for example by Einat, she showed us that we also have a theoretical background for exactly this deformation at stress and strain rate fluctuations. So there is some mathematics known for that area and for that behavior. And but what is the other evidence that we have on postseismic creep? And for example, we have the geodetic record where we have, after a major earthquake, accelerated surface deformation. And there are, of course, several things discussed, which are the reasons, which could be the reasons for this accelerated surface deformation following a major earthquake. And that is here from Pelzer, 1997, for the deformation after the Landers earthquake, which happened in June 1992. And this is the accelerated surface deformation covered within a time frame from 1992 to 1996. So we do have surface deformation after the earthquake, but there are several explanations for that. Do we have aseismic fault creep, rupture propagation, which is slow and aseismic, as we heard yesterday? Or is it relaxation at the base or below the base of the seismogenic zone? So yeah, we have the surface information, we don't know what is happening down there. What is the seismological record? Just one example here, what it was observed again after the Landers earthquakes, and that is from Rolandone et al. 2004. So after major earthquakes, people observe that the aftershocks occur at greater depth. So we do see, following a major earthquake, within a long time frame, within years, we see that the hypercenters of aftershocks are firstly shifted to great depth, and then they are moving upwards again. So that is one seismological evidence that something is happening in the deep, that we have. So one explanation would be that we do have a fracture system. We have increased pore fluid pressure or fluids available in that area, which then heal. So we firstly shift the brittle ductile transition to greater depth, and then it's restored again by healing of fractures, by healing processes following this major deformation. Then there are numerical models that try to get hand on that area which we cannot access directly. Yeah, we have all the observation evidence is somehow indirect. So what do the numerical models show? And that is one of the earlier models from Ellis and Stöckert. There have been several others after that by the group of Nüchter and Ellis and Stöckert and Ellis. So they model the stress redistribution below the seismogenic zone. And so what they find is that we do see areas of increased differential stress, of increased strain rates, and so that is occurring in these models within hundreds of years, for example. So are these observations and are these numerical models valid or not. So we always have to make the proof by the natural observations, by the natural system. And but we have in the natural system always a problem that also this information is also only indirect. And the information of the natural system involves always a history of different processes. So we cannot isolate the different processes of coseismic loading, postseismic creep in the natural system. So that's why we also did some deformation experiments. And so the deformation experiments wanted to simulate the natural stress history. They didn't want to simulate earthquakes, but the natural stress history that is occurring within the base or below the seismogenic zone, and to isolate the different processes of coseismic loading or coseismic deformation in that area, and then the postseismic creep following that one. And what we did is we did high stress experiments, so we call them kick experiments, where we were able to basically do the experiments at more or less in situ conditions. So we did not really need when we compare that to the natural record, we don't really need to extrapolate here. So we can do the experiments at nearly natural conditions. So we have here 400 degrees Celsius. We have high strain rates. Well, you might argue 10 to the minus 4 per second is not that high for experiments, not. Yes, for nature it is, but it is probably more or less considerable to natural deformation rates in that area coseismically. So we have high stress deformation at these moderate temperatures, and that is our kick stage to simulate the coseismic loading. And then we have two different following stages. The cook stage, where we just remove the piston and anneal quasi-statically. And then we to model relatively fast stress relaxation. And here we increase the temperature. So here we have to extrapolate. We do the trade temperature against time. So we just increase the temperature to accelerate the processes, not because we think in nature we have elevated temperatures. We stay at more or less the same temperature level for the natural system, but we just speed up by increasing temperature for that stage. So we have a kick and cook history, stress loading and fast stress relaxation, and then we have a creep stage which is modeling the relatively slow stress relaxation. And in nature, of course, whatever is a stress relaxation, it's on the one hand, of course, a deformation which dissipates the incoming energy stress, but then it's of course also the tectonic setting, the far field stress, which is set by the tectonic setting. So that is controlling the stress relaxation in nature, and it can be fast, it can be slow, and whatever that is in nature. So we did that in the experiments first, and then I come to the natural observations to compare that. So that is from our kick experiment, so no annealing afterwards, we just quench it after the high stress deformation. And what kind of deformation can we expect at the base of the seismogenic zone? We do see fractures, so that is basically the rim of a fracture. And here we see an area which is strongly distorted. So that is a TM foil prepared by the focused ion beam technique, and so that is a bright field image in the TM. And we do see here at the rim of such a fracture, we do see an area which is strongly distorted. So it's tiny microlites which have a more or less random crystallographic orientation. And so this is here just only very close, very localized and very heterogeneous deformation along such a crack. But then if you go some distance to the crack, we basically see an undistorted crystal. So we have strongly localized deformation, glide controlled fracturing, so it's a combined fracturing and dislocation glide controlled deformation, low temperature plasticity, what we heard yesterday and already on Monday. So These are some areas outside of that area. So we have fractures and this microlites here. We have a high amount of dislocations, but then we also have these tangles, this dislocation forest, and that is of course strain hardening. We increase the dislocation density dramatically, so we have a lot of stored elastic strain energy. So we have put a lot of strain energy in our system, and which is stored within these microstructures. And we do see, and that's highlighted by these arrows, we do see within this forest areas that have a low dislocation density. So we call that a cellular structure, which means that we have cells of low dislocation density covered by a high dislocation density crystal volume. And then we have also these microlites. And these are, of course, very important sites for the annealing afterwards. So what is happening with exactly these sites during annealing, during the cook stage? And then we do see growth of new crystals. And these have a completely different crystallographic orientation than the host. So they somehow lose the crystallographic orientation, so it's not a bulging, it's not only subgrain rotation, but of course it must be something like subgrain rotation. So we have these cells that lost somehow the memory of the crystallographic orientation of the host and crystallize with a new crystallographic orientation. So we see localized strings of recrystallized grains within large deformed host grains, and that compares very well to nature, what we observe in nature as well. So these are samples from the experiments, and this is a sample from vein quartz in the Long Valley caldera in California, and we do see very, very similar microstructures. So that gives at least some indication that we address the same processes in the experiments than we do in nature. What is if we don't isostatically recrystallize? What is happening when we still leave a little bit of stress on our sample, which is probably a more common natural more common natural case, that we do leave a little bit of stress on it and that we have relatively slow stress relaxation. And that is what we simulate with our kick and creep deformation. And here is again an example from the experiments. This is an example from nature, and we do see again very similar features. We do see strongly localized deformation and recrystallization. So we have again this areas where we increased the stored strain energy during the kick event, and then these are areas of recovery and recrystallization during creep. And so we do see high dislocation density. We see dislocation walls in these areas where we see something similar than deformation lamellae, but it's just again recovered low temperature plasticity basically. So it's low temperature plasticity, but additionally some recovery in this area. So we still also probably nucleate further deformations, further dislocations, so that we end up with these deformation lamellae or areas of increased dislocation density that switch and change with areas of lower dislocation density, although in this natural example here, where we have these dislocation walls, this is not an area of low dislocation density, it's just a different diffraction contrast. So if you tilt it a little bit, then here the dislocations will pop up and here the dislocations will disappear. So it is a high dislocation density also within this rock here. So obviously, so within the host crystal. So obviously during creep we not only localize the deformation in the highly damaged zones, but we also have some deformation in the host rock. But then here within the areas of high dislocation density introduced during the kick, we see the major recrystallization going on. So we summarize that. Kick and cook and kick and creep history. Here we have fast relaxation. Here we have slow relaxation. The kick is always the same. We introduce highly damaged zones with a high dislocation density, with this forest cellular structures. So we zoom in this area, so we see this cellular structure somehow. And then we, during the cook and creep stages, we see generation of low angle grain boundaries, and then finally high angle grain boundaries that then make new grains. So during the kick, we have, as Patrick showed on Tuesday, we have this stage of very high density, velocity of dislocation glide. So we just produce dislocations on and on and on. But they are hindered in glide because we get this forest, so we get strain hardening, some fracturing going on. And when we decrease the stresses, although the temperature, pressure conditions stay the same, we change the velocity, the relative velocity between dislocation glide and climb. We are able to recover and recrystallize, which was not possible during the kick stage. So we change the relative velocity of dislocation glide and climb and have effectively recovery going on here and recrystallization, whereas here is just basically dislocation glide and fracturing. Low temperature plasticity, creep. And whether we have high stress relaxation, we do not see deformed new grains, so the new grains are pretty much stress-free. If we have relatively slow stress relaxation, we see deformed new grains, so the grains are deformed. Okay, so now that are the experiments, that are the indications from the other disciplines. So what further information can we get from natural shear zones? What further information can we get from the natural system? So of course we don't have the full story with these indications. So we have a lot of open questions. We try to get, so what are the numbers here? What is the high stress? So we have, from the natural system, we do have some evidence that we reach like 500 megapascal or even higher from paleopiezometers of pyroxenes, for example. And what are the rates that these high stresses are, what are the loading rates? It's probably more important to talk about loading rates when discussing this kick than strain rates, because the strain is probably very low, the overall strain. Of course, we introduce a high stored strain energy very locally in our system, in our rocks, but in our crystals. But the whole strain that the rocks see is very little during that stage. The high strain is coming here during this postseismic stress relaxation. So what are the rates of stress loading? And that is probably that's probably determined just by the slip event within the seismogenic zone. So within the seismogenic zone, we have the rupturing, and within this rupturing, we load the plastosphere. And so that is probably within seconds and minutes that we come from the background stress that is set from the tectonic setting to the peak stresses, which only prevail very transiently, and then they relax. But what is a relaxing history? So what are the timescales here? So the timescales are, for the stress relaxation, are much more difficult to get. They are governed by deformation, of course, but then also by the repeat or the background stress that's acting on our rocks. So it's the tectonic environment that is important. Okay, so I think we have to look at the natural system again, and we miss another thing as well, of course, and that is the pore fluid pressure. So we miss in our experiments. It's pretty difficult to incorporate also fluids. When we have to increase the temperature and put fluids into our system, we probably really change the processes, and it's not comparable to nature anymore. So here we really have to rely on our natural system. So we increase the porosity, we drop increasing porosity, so we drop the pore fluid pressure coseismically, because otherwise we wouldn't even be possible to get such high stresses. And then during postseismic relaxation, we heal and seal our fractures and damage, so that we change and we control our postseismic creep. And again, people say, well, because we have so little strain during this kick stage, it's not really important. Why should we bother? It's not much strain, during the kick experiment, but still it controls what is happening afterwards, because we increase the strain energy so dramatically. So the high strain is coming here, so this is, in terms of strain and strain rate, of course, the more important process. But still, this here controls what is happening here. So this is important also to consider. Okay, so now what questions do I want to address with the natural system of this DAV shear zone that is in the title? So I would like to talk about the episodic availability of fluids. So do we have metamorphic reactions happening? So do we have a lot of fluid inclusions in different parts of the microstructure? And of course, we do also have evidence of large-scale quartz veins within shear zones commonly. So that is also apparent. I want in this talk to address rather this fluids and metamorphic reactions in fault rocks and not in the quartz veins, but they are also there, and so they also record these processes at the tip of a propagating zone. So we do have the fracture zone, and we basically look at the process zone of such a seismic active fault. So we are looking here in this process zone where we have the stress and pore fluid pressure fluctuations. Then what is the influence of the tectonic regime? So if we talk about the stress relaxation and stress loading, what are the stresses? They are probably very different, or systematically probably different for different tectonic settings. We might expect during thrust fault settings higher stresses within the base of the seismogenic zone than for normal faults. So what are the stresses, and what is the difference for the tectonic regimes? Do we see systematic differences? And then another thing, of course, linking to the long-lived activity of shear zones. One shear zone is not made out of one earthquake, definitely, so we have repeated cycles. So what are these repeated cycles? Do they show up in the rock's record? What is a rock record of these repeated cycles? Do we broaden our shear zone, or what are the controlling factors there? And one other slide before I come to the DAV. This is a model of a thrust fault regime from Nüchter et al. 2013, and they show nicely that the deformation that we are looking at one site of observation, so if we talk about the rock record, we have one site of observation, so it's this record that we are looking at. And if we talk about major shear zones, then we have to assume that we don't have just one rupture, but the rupture is acting on several time increments, and so we have a propagating rupture front. And if we look at one rock, we might see deformation dependent on the distance to the propagating rupture tip. So we might see systematically in the rock's record, firstly deformation far away from the rupture zone, and then finally we do see the rupture zone crossing our rock record. And so in that specific setting of thrusting, the major outcome also from this paper was that we do see the last stage are the pseudotachelites. And the pseudotachelites are not kicked another time because the rupture front just passed. And after that, we have relatively low stresses, but high strains. So we might still have high strains, right? We might deform our pseudotachelites, but not within another kick, not with another high stress event, because the rupture front just already passed and the area is now weak. And so we do not kick our pseudotachelite once more. So pseudotachelites are commonly the last thing of this propagating zone that we do see. But that is for thrusts. So what is the dependence on the other tectonic regimes? And the example I would like to show you today is from a shear zone that is a steeply dipping strike-slip shear zone in the Eastern Alps. And it's exactly, so the most fault rocks show that the deformation occurred at green schistofacious conditions. So it's exactly this base of the seismogenic zone that we are looking at, 300 degrees and a little bit more. So I would like to show you the mylonites from this shear zone. And so this is one, very exceptional mylonite maybe. So we do see a very strong foliation, and we do see shear bands within these rocks. So a strong lineation, strong foliation, and a shear band cleavage. So a second foliation. So what is the microstructures looking? So we do have here a thin section where we have this foliation showing. Then we do have here our shear band cleavage. And then we do see other microstructures like bookshelf structures. So this is a garnet. So a garnet strongly fractured and smeared away. And then we have these shear bands, and all point to a sinistral sense of shear. So consistent shear sense indicators. This is just a micrograph taken with compensator plate inserted to show you that we do have a strong crystallographic fabric. So that's basically all quartz. And quartz shows with this compensator plate, because we do have relatively homogeneous colors here, that we have a homogeneous crystallographic orientation in a few parts of the rock microstructure, but in a few parts we have systematically different crystallographic orientations. So the task now is, from this rock, do we see several kick events? Do we see a time-dependent rheology here in this rock? So we have to zoom in a little bit, and we zoom in here with SEM. We have here band contrast image, and we do see that we have different domains that was already visible with the optical microscope. But here we see some other features. We see that we have strongly increased porosity in the areas where we do have the shear bands. And we see these strongly elongate quartz grains. So they have a really amazing shape preferred orientation and crystallographic controlled preferred orientation. So the aspect ratio is, sometimes even up to 20 or so. So amazing long and big quartz crystals that do show like a whole bunch of deformation, internal deformation structures. But then here our fine-grained area is very different from that by the high porosity that is highlighted here. Okay, so what is the crystallographic orientation? To measure that, we look at the EBSD, and we measure the crystallographic orientations, which is although already visible from optical microscopy. So we do see here these strongly elongated grains that have a markedly different crystallographic orientation, and that is more or less just dark in the optical microscope, pointing that we have the C-axis perpendicular to the thin section. So it's this Y maximum. We have, of course, the axis of the strain ellipsoid, of the finite strain ellipsoid, are a little difficult to estimate if you have these shear band cleavages and foliations, but we just assume that the finite strain ellipsoid, we have the foliation is giving is the plane where Z is perpendicular to, and X would be the lineation. So that are just the axes of the finite strain ellipsoid, and then we do see here a Y maximum for our elongated quartz crystals. So elongate quartz crystals, the Z-axis oriented more or less parallel to Y, so that would point to dislocation glide with the system prism A glide. The grains within the shear bands have a different crystallographic orientation. We do see a large scatter though, but they are rather at the hemisphere. So that would point to a different deformation mechanism, different history than our elongated quartz crystals. So yeah, and maybe basal A glide. So what we do see we zoom in within these little quartz shear zones, we do see a systematic difference. So when we have sinistral shear zones, we do see rather a C-axis that is also moved to the sinistral side. And in the dextral shear zones, we do see a systematically different crystallographic orientation. But still, we have the problem, what controls the crystallographic orientation of these grains? Is it dislocation glide, really? Or is it some nucleation and growth process with the C-axis perpendicular to the shear bands? Or is it just rigid body rotation? So there are a lot of different options that can be discussed here. And it's not fully clear what kind of processes are involved within that area here, just from looking at the crystallographic orientation. So we go into the TM and to distinguish whether there are dislocations or not, whether we do have some evidence of crystal plastic deformation. And yes, they have in some parts at least, they have a moderate high dislocation density, the new grains, so they are obviously also deformed, the new grains, and that would point to a creep process. Yeah, so we have dislocation glide and recrystallization going on, but then we also have this high porosity along the grain boundaries. We do see domains of low dislocation density, and very small grains, like a few microns in diameter. So that would point to dislocation creep, but then we also have other areas where we do see, again, high amount of cavities and pore fluid, or like fluid inclusions along the grain boundaries. And we do see a nice foam structure with 120-degree angles. We see isometric grains, and they do not show any internal misorientation. So somehow this microstructure would rather point to strain-free new grains, which are not deformed. So obviously we have different domains, differently deformed domains. So here we have some evidence that after dislocation creep, even the grain boundaries were controlled by the reduction in surface energy to make this a nice foam structure. So that would point to nearly almost static conditions at some point in specific areas. Okay, so to summarize the quartz microstructure, well, we have different stages or different populations, I should say, and can we relate that to different stages? That is, of course, always a question from the natural system. So we do see the layers of elongate quartz grains, prism A glide, which points to dislocation creep. Then we have the extensional shear bands, where we, of course, must have some brittle deformation involved, but also some crystal plastic deformation, nucleation and growth associated with this dislocation glide. And finally, even grain growth at quasi-static stresses. So we think we do see a systematic difference in different deformation mechanisms, deformation processes, and behavior, and we link that to a time sequence. So, but to get that, what do the rock is not just quartz. So what are the other minerals doing, and what is with this fluid flow and metamorphic reactions? This is another SEM image, and we a little bit larger scale. So we have here the quartz matrix, and we do see here the shear bands. And along the shear bands, we do have biotite. And that already indicates that the temperature conditions are not completely different to the green schistous conditions that we have otherwise in the rocks. So the shear bands, if there is biotite stable, are not very late features that are just during exhumation. So there are still at green schistous conditions. So the shear bands is not in terms of metamorphic conditions, not a very late exhumation feature. Then we do have the garnets, and they look very amazing as well. So we do have fracturing of the garnets, and then this bookshelf structure indicating the rotation of these shattered crystals, and they are here disintegrated along these shear bands. So what is showing the EBSD and EDS from this area. So we have a relatively homogeneous chemistry of our garnets. We have slight differences at the rim of the garnets, rather indicating that the garnets were not really unstable during the deformation. Probably they didn't grow, of course, but still it's not very late deformation otherwise, and not high pore fluid pressure. Otherwise, the garnet would have reacted to chloride and so forth. The garnet was shattered probably during a very high stress loading event where the pore fluid pressure was initially relatively low. So we increase the stresses, drop the pore fluid pressure, and shatter the garnet at a stage where we did not have a lot of fluids. But then when the stresses relax, also the fluid pressure comes in there, and we have the creeping matrix around the garnet, and that's how the garnet then is rotated to form these bookshelf structures. And the EBSD patterns show exactly that. So we have, of course, a variance of different crystallographic orientation, but that is simply due to rigid body rotation. Okay, so then we want also to somehow get an idea of the timing and other metamorphic reactions, and we do see monazite crystals that reacted within these rocks. And we have, for example, here a monazite inclusion within a tourmaline, and the reaction here is very little. The monazite is quite fresh and homogeneous. We just see a very small rim of apatite and allanite surrounding it. But then we see also here a crack moving through our tourmaline. So whatever induced the crack, was the crack there and then fluid introduced and triggered the reaction, or was a reaction going on triggering the fracture? We don't know. We don't know, but what we know is that if we see the monazites within the matrix, a rather open system, we see like major coronas around, so the reaction, a lot of more reaction is taking place within the rock matrix, where we not have the container of our tourmaline. So obviously the reaction is triggered by deformation, so the corona structure is elongate, and much more, the reaction started much more, and even sometimes the monazite disappeared. Well, of course, that is a little bit of a problem of 3D section, but still the monazite is much more transformed into this, into the other mineral assemblage. So the monazite is basically still a single crystal, a little bit variation, but then nothing really severe. And the apatite and allanite do have no any apparent systematic differences in or systematic relationship in crystallography. But that is not important in the moment. Why are the monazites so interesting? Because we can date them, and that's what Emily Janotz and colleagues did. They dated the monazite, and Pierre Lanari also dated the epidote and allanite. So what we do get is an age of about 50 to 70 million years, so they are not old features. not very old features anyway. And so we do see, especially, this corona microstructure is not strongly deformed, although, of course, we have a shape-preferred orientation of the corona, which has nothing to do with the shape-preferred orientation of the monazite. The corona has an elongate shape, which is obviously not dependent on the, or probably not dependent on the original shape of the monazite. So, but now what is within our, what is with the larger picture? What is the monazite in our mylonite? And we do see here, so in the optical microscopy, the monazite and corona structure is not that apparent. That's why I put on this SEM EBSD image on top of it. So the monazite corona obviously was there already when the shear bands formed. So we can use metamorphic reactions and deformation processes to get the timing, the relative timing and conditions within our rock. So obviously the corona formed with elongate shape when making the main foliation, the first foliation, but it has been there when the shear bands formed, because you clearly can see the quartz is strongly deformed where we have high stress concentrations around that corona, and in strain shadows or stress shadows the quartz is coarse or great. Okay, so coronas formed during probably the formation of the main foliation, but before the shear band foliation. And so I now come to the last part. So we have here also cracking of our corona structure, and within the cracks we form biotides. So again, the conditions of the cracking were at green schist facies conditions. So it's not a purely late cold fracturing that is going on. So fracturing at the base of the seismogenic zone where we have otherwise ductile deformation. So what do we see if we come back to our stress and pore fluid pressure and time sketches? So we see that we have a deforming rock, creep and metamorphic reactions going on. And then we have a kick event where we form fracturing within the quartz, formation of the shear bands during shearing, and cracking of our garnet, and then the rigid body rotation during creep. So we do see brittle deformation also in garnet, in the coronas, in the quartz, in any, so the whole rock probably fractured and healed. Yeah? So we have the kick, fracturing, dislocation, glide, control, deformation, then creep and metamorphic reactions going on. The question now is, do we see one or more kick events? And what about this process here? What is with the first foliation? Is that a kick or is it not a kick? And we would argue, I would argue, yes, it is also a kick, but at probably not that high differential stresses and at a different distance to the crack tip of the seism. So yeah, just a deformation dependent on the distance to the seismic rupture zone. And so I would argue, yes, this foliation and dislocation glide controlled prism A glide is also a transient episodic deformation, because it's not steady state creep. In steady state creep you would expect other microstructures than these amazingly elongate quartz ribbons. And then another thing, and that's the final microstructure I'm showing you. Well, we also in some areas localized see this kind of features, breccias, cataclasites, and maybe even a little bit of, well, it's sometimes a little difficult to tell cataclasites, pseudotachelites, but we have breccias that are made of mylonitic components. And so that definitely, I think here everybody would agree that is a kick. And the latest stage of kick here, we do have fracturing within the components. Of course, we have cataclastic deformation in the main matrix of this rock. So that is probably the last kick where the rupture front just hit our observation site. Yeah? So we have one observation site. That is basically most of the microstructures really come from one rock. And so we have one observation site, and we do see deformation, which we interpret as dependent on the deformation dependent on the distance of the tip of the rupture zone, which is propagating through the rock, and the final kick is a very rapid stress relaxation. And here we have slower stress relaxations in the first kicks, but that is also here probably not that different from a steady state creep anymore. Yeah, we think we still have some stress fluctuations, but this is not far away from steady state creep. Whereas here we have marked differences in glide control deformation and creep, and here we just have cataclasis and then a little bit of relaxation going on. So I thank you for your attention.